even though a program may produce the correct answers, we may have at least gone through all the debugging, we may have it working for a couple of data sets, we still need to make sure that the program is 100% correct. So how do we make sure it does work on all data? Well, there are a couple ways we can go about this, and one approach is what we call empirical testing. So the idea is that we would design a special set of test cases. This is what we would call a test suite, and then we would run the program using this special test data. Now, the test data itself would be carefully chosen to make sure we check all the different logic paths through a program to see if we can uncover any errors. So, like for example, let's say we have a conditional statement. One set of data would make all the Boolean expressions true. That way we can check those blocks of code. Another set of data would make sure that the same Boolean expressions would be false, so we can check the other block of code. Now, I mean, the quantity of the test data doesn't matter. What matters is that we cover all the various test cases. So the goal of empirical testing is that we make sure that every statement in the software has been executed at least once. Now, we should note that in all but the most trivial programs, it's not going to be possible to cover every single possible case. But the best we can do is just say that the more thorough the testing, the higher chance that we're confident that our program is correct. Now, it's not a good idea to wait until the program is complete before you do any testing. In a problem of any size, it's too late to identify where an error occurs. So there are other different types of testing that we can use to help us during the implementation process. So unit testing will take place on each module or subtask code as it's completed. Now, as each of these tested modules are combined to work together, integration testing is done to make sure that the modules communicate the necessary data between and among themselves, and that all the modules are working together smoothly. And then finally, if anything is changed on any already tested module, we can use regression testing to make sure that this change hasn't introduced a new error into the code that was previously correct. A second and totally different approach to confirming a program's correctness is the use of mathematical logic. So we use what's called program verification, and this can be used to prove that if the input data to a program satisfies certain conditions, then after the program has been run on these data, the output data would satisfy certain other conditions. Now, this isn't a magic wand that just gives us blanket assurance that the program will absolutely behave as we want. It's also worth mentioning that the program verification process can be a difficult and time-consuming process. That's why program testing is used a lot more than formal program verification to reduce the risk of program errors. In addition to correctness, the problem specification may require certain performance characteristics, such as the amount of time to compute the results. This is where benchmarking comes into play. So benchmarking the program means that we will run it on many data sets, and this is to make sure that its performance falls within those required limits. At the completion of the testing or the verification and benchmarking, we should have a correct and efficient program that is ready for delivery. Now, of course, all the testing, verification, and benchmarking results are committed to paper as evidence that the program meets its specifications. So once again, we do need a document that verifies that we did make sure that the program is correct and we did go through all the benchmarks. Program documentation is all of the written material that makes the program understandable. So, I mean, this is a very tedious task, but it is absolutely necessary to make sure we include all the important documentation. That way, not only do we remember how a program works, but if we need to pass it on to someone else, they would have an idea of how the program works. So this includes several different types of documentation. So we first have internal documentation, which is part of the program code itself. So it gives the proper names, it gives the comments. I mean, good internal documentation would consist of choosing meaningful names from program identifiers, using plenty of comments to explain the code, and then separating the program into short modules, each of which would do a specific subtask. We also have external documentation, and this consists of any materials assembled to clarify the program's design and implementation. Now, I mean, we have put this step rather late in the software development process, but I think I've kind of mentioned several times before that each preceding step would produce some form of documentation. So, I mean, program documentation goes on throughout the entire development life cycle process. It's not just, okay, the next step is documentation. Write all the documentation here. No, we talked about in the previous steps that at the end of this step, we have this document. At the end of this step, we have this document. So, I mean, when we're doing these materials, when we're doing this external documentation, we need to do it for all of the documents that we have previously discussed. Now, the final finished program documentation is written in two forms. We have the technical documentation, and this allows programmers who later have to modify the program to help them understand this code. So such information as structure charts or class diagrams, description of algorithms, and program listings would fall in this category. But this is the documentation that helps programmers understand what is going on here. And then finally, we would have the user documentation. So this helps the users run the program. So I mean, this would include online tutorials, answers to frequently asked questions, help systems, and even user manuals. But this is to help the user actually run the program. Now, programs are not static entities that once they're complete, they never change. Because of the time and the expense that's involved in developing software, successful programs will be used for a very long time. I mean, it's not unusual for a program to still be used 15 or 20 years after it's been written. I mean, take a look at something like Microsoft Office. I mean, it was developed back in 1983, and it's still being used to this day. So, I mean, in fact, a typical life cycle for a medium to large size software package is about 1 to 3 years in development and 5 to 15 years in the marketplace. So, I mean, that means that we need to make sure that they're updated to work properly on newer systems. I mean, and during this long period of use, we may encounter additional errors or additional bugs during this time. So, I mean, we got to make sure that we're ready to make changes and to make sure that they're working for these new environments and we get rid of these bugs. So the original program is going to need to be modified and brought out in new versions to meet these changing needs. So this is where program maintenance comes to play. So program maintenance is the process of adapting an existing software product. And this may consume as much as 65% of the total software development lifecycle budget. Now, I mean, if the program has been well planned, carefully designed, and well coded and thoroughly tested and well documented, then the maintenance is going to be a much easier task. But, I mean, it's still a very important step. So, I mean, that's why I've been saying for so many times here that how important it is to take these earlier steps seriously. Because if we do the early parts correctly, then when we come back to having to make these updates, it's going to be very simple. But if we haven't done it correctly, then this is going to be a very daunting, a very tedious task. And I should also mention that the maintenance is not really, it shouldn't be viewed as a separate step in the software development lifecycle. It's not, okay, we go through all the steps, last step is maintenance, and that's it. No, this actually usually involves the repetition of all the steps that we previously described. So whenever we need to make a change to the software, we would still need to do a feasibility study. We would need to do a problem specification, program design, algorithm, writing the code, debugging, testing, verifying, benchmarking, documentation, all that. So we usually have to go through this entire cycle again every time that we're fixing issues or we're making updates to our software.